Okay, let's talk about section 6.6. Logarithmic and exponential equations. Okay, so we have logarithmic functions. The logarithm to the base a of x. This symbol, this very complex symbol, just means a to power y is equal to x. We're looking for the exponent. And we also know that in order to make this a logarithmic function, or in order to make this exponential function reasonable, we require this a greater than 0 and a is not equal to 1. So this is a setting. So by this condition, remember we have two types of our exponential function. One is increasing, the other one is decreasing. So we have two types of our logarithmic function also. Okay, so this is our idea. Remember, in the most cases, we cannot directly evaluate the value of a logarithmic function. We always translate a logarithmic function to the exponential function and try to evaluate. Okay, and in the logarithmic function, we have two special base. One is ln. ln of x is log to e of x. This is one special symbol. The other special symbol is just log x. Log x means the logarithm to 10 of x. Okay, so there are two special symbols. And for example, if we have log to 2 of 1 minus 2x, if it is equal to 3, for example, let's just pick up simple one. If it is equal to 3, then by the definition, 1 minus 2x is equal to 2 cubed. 2 cubed is 8. So negative x is equal to 8 minus 1 is 7. You move 1 to the right side, it is 8 minus 1 is 7. So x is negative 7 halves. You see, we always do this, the translation. We don't directly solve log. Okay, good. And sometimes if you have logarithm function on two sides with the same base, log a of m is equal to log a of n, then we know that m has to be n, has to be equal to n. Okay. Okay, let's keep this in mind and we try to do the computation. And for example, solve 2 log 5 of x is equal to log 5 of 9. Okay, we'll start from the simple one. How do we do that? Logarithmic function has a property. If you have coefficient, you can move it forward, inside. You can move it inside. So log 2 5 of x is equal to 2 log 5x is equal to log 5 x squared. 2 log 5 of x is log 5 of x squared, and it is equal to log 5 of 9. Okay, now you check. You have a logarithmic function with base 5, and you have x squared equal to 9. So x squared is 9. That's what this property tells us. X squared is equal to 9. What is x? You have two choices. X is positive square root of 9 and x is negative square root of 9. because originally x is inside the domain, of log 5 of x. It is in the domain, so x is positive. Remember that the domain of a logarithmic function is a positive. It's a set of all positive real numbers. Okay, so here you can only choose the positive square root, the principal square root. So we get x is equal to 3. X is equal to 3. Okay, so this is the first example. Second, solve the logarithm to the base 5 of x plus 6 plus the logarithm to the base 5 of x plus 5 is equal to 1. The sum of the two logarithms to the same base is equal to 1. The sum of logs is equal to the log of the product. Remember that? Log am plus log an is equal to log am times n. Okay, so this is the property. So here we apply this property to the left hand side. We get log 5 x plus 6 log 5 x plus 6 times x plus 5 product, and then apply the logarithmic function. It is equal to 1. Okay, so first we combine the sum together into one logarithm to the base 5. Okay, and then remember we have two important evaluation. First, log a of 1 is always 0. This is one computation. The other one, log a is equal to 1. Log a1 is 0. Log a is 1. So here logarithm to 5 of this expression is equal to 1. X plus 6 times x plus 5 is equal to 5. Okay, so it's g equal to the base. The product is equal to 5. We cannot solve it directly. Okay, so let's multiply the left side and simplify it. So you multiply it out, it's x squared 5x, 6x, 30 is equal to 5. So x squared plus 11x is equal to what is this? It's 25. Okay. Wow. I see. Because with this, there's no solution. There is a solution. Okay, but this one we cannot factor it. There's no factorization. Let's try the root formula. Root formula, x is 2 negative 11 plus or minus square root of 11 squared minus 4ac. Okay, it's not extremely bad. So it is equal to 11, negative 11 plus or minus 11 squared is 121. 4 times 25 is 100. 121 minus 100 is the square root of 21. Square root of 21. And so we have two solutions. So x is negative 11 plus square root 21 over 2, or x is negative 11 minus square root 21 over 2. The situation is, are they both the solutions? Remember here, we have x plus 6 and x plus 5 from the beginning. So x plus 6 and x plus 5 are in the domain of logarithm to 5 of x, in the domain of this logarithm function. So x plus 6 is greater than 0, and x plus 5 is also greater than 0. x6 plus greater than 0, x is greater than negative 6, and x is greater than negative 5. So let's check. Negative 5 is here, negative 6 here. It has to be greater than this, it has to be greater than this. So it's an and. And means two conditions are satisfied together. So x is greater than negative 5. You have to choose this part. Okay, the overlapped part, because you choose and. X is greater than negative 5. Let's check this. Let's check this. This value, especially this value. Negative 11 minus square root of 21 over 2. 11. Let's put a negative 10 minus 1 minus 22. Negative 10 over 2 is a negative 5, and a minus. Okay, so negative 5 minus 1 plus square root of 21 over 2. This one is less than negative 5. It's negative 1 and minus a positive number, so it's less than negative 5. So this is not in the domain. And the other one is in the domain. The other one, and negative 11 plus negative 11 plus 21, negative 21. It is, we do the same thing, negative 10 plus 21 minus 1 over 2. It's a negative 5 plus root 21 minus 1 over 2. It's negative 5, but at this moment you add a positive number, so it's greater than negative 5. You add a positive number. How do we know it's a positive? Square root of 21, of course, it's greater than 1. Greater than 1 over 2 is a positive number. Negative 5 plus a positive number is greater than 5. So the solution is negative 11 plus square root of 21 over 2. Only one solution. Okay? There's only one solution. Next. Solve natural log of x is equal to the natural log of x plus 6 minus the natural log of x minus 4. Okay, so here the natural log of m minus the natural log of n is equal to the natural log of m over n. The difference of the logs is equal to the log of the quotient. Okay, so the right hand side is equal to the natural log of x plus 6 over x minus 4. Okay, natural log is equal to the natural log You drop the natural log, you only get x is equal to x plus 6 over x minus 4. X plus 6 over x minus 4. And when we just solve this equation, we multiply two sides by x minus 4. We simplify this equation, so x squared minus 4x is equal to x plus 6. So move all terms to the left side. X squared minus 5x minus 6 is equal to 0. So x minus 6 and x minus plus 1 is equal to 0. So we have two solutions. So x is either 6 or x is negative 1. Okay, 6 or negative 1. But x is in the domain of natural log of x. So x is positive. Negative 1 is not a solution. It's not a solution. So there's only one solution. 6 is a solution set. 6 is a solution set. Okay, so every time when you after you solve the logarithmic equation, you have to check if it satisfies the condition of the original equation or not, because the logarithmic function has a domain only for positive numbers. Okay, so if you have a polynomial functions or if you have exponential functions, it's fine. You don't have to check your solutions every time, because they have domain from negative infinity to positive infinity. You get whatever value, it does not violate the domain. But a logarithmic function has a smaller domain, only for the positive numbers, so you must check it. Okay? So this is a logarithmic function. Then let's talk about exponential function. Exponential function, again, we have the relation. Okay, so that's one of important. We have the relation between exponential function and the logarithmic function. That's one of the most important trick to solve the exponential equations. And plus, if a to u is equal to a to v, then you get u is equal to v. U is equal to v. Okay, so that's very important. Those two concepts are both important. First, let's start from the simple. Solve a 2 to x is equal to 5. If 2 to x is equal to 5, this is a typical example for the definition of a logarithmic function. You know the value, you know the base, you're looking for the exponent. That's the purpose of the exponential function. So x is logarithm to the base 2 of 5. Okay, if we just want to find the exponent, you just use a definition of logarithmic function. B, if you have 8 times 3 to x is equal to 5, for example. Well, first you divide two sides by 8. You get 3 to x is equal to 5 over 8. And then you apply the logarithmic function. So x is the logarithm to the base 3 of 5 over 8. And that's it. Okay, you can just leave it like this. You don't have to simplify it. You don't have to simplify it. Okay. In the textbook, they choose a special way, but there's alternative way. They choose alternative way. It's not useful. Just use this. Just use this. This is enough. The alternative way. Let me explain the alternative way. For problem A, the same thing. Alternatively, it comes from the following idea. Remember that the logarithmic function for whatever base, m to r is equal to r times log to m, or log to a of m, log to the base a of m, logarithm to the base a of m. So it can move this exponent down. The reason we cannot solve it directly is that it's on the shoulder. It's not in the same row. It's not on the same row. You cannot do anything. And by the logarithmic function, we can move it down and make it in the same row, and then we can do the addition, subtraction, multiplication stuff. So here we apply the natural log. You can apply any the log with any base, but normally we choose the natural log. We apply the natural log on two sides. And then by this property, we can move x forward. See, it becomes a coefficient times x is equal to another number. It's like ax is equal to b. So x, a, b, they are in the same row. Then you can do the division. So x is log 5 over log 2. And this value is equal to log to the base 2 of 5. This is a change of base formula. Okay, so they have different idea. This one, we just directly apply the definition of a logarithmic function. And this one, we try to move the exponent down and then apply the addition, multiplication, or subtraction and division stuff. You can do both. You can do either. You don't have to do both of them. Just do either of them. And the advantage of a logarithmic natural log function is that we have some table in the engineering part, or in the computation. We do have some quick way to compute the natural log of 5 and natural log of 2. If you have any, like for example, if you have a natural log to the base 1.4 to 2, something like that, it's difficult for you. I mean, not difficult. It will take time for you to find the value. So that's why we like the natural log. But it's okay. For our pre-calculus and the calculus study, this is a perfect answer. Okay, this one is good enough. This one is also good. Okay, you can put either of them as the answer. Okay. So remember, whenever we try to solve logarithmic equation or the exponential equation, we need the same base. Okay, we need the same base. This time, let's see if we have different base. For this one, you can do the first type or the first method or the second method. You just, for example, if you consider the first method, 5 to the exponent is equal to this number. I don't care what this number is. This is equal to this number. Like 2 to x is equal to 5. Then you check that by the definition of the logarithmic function. The logarithm of to the base 5 of this value is equal to x minus 2. Okay, so it's like this. 2 to x is equal to 5. This complex expression is a number 5 in the previous example. This 5 is a base in the previous example. So, okay, and then you apply the property. You can move this exponent forward. So you get 3x plus 2 log 5 of 3 is equal to x minus 2. And then let's try to simplify it, because now x and all the numbers are in the same row. So you can do the linear computation. So it's 3x times this plus 2 times it is equal to x minus 2. And I'm going to move x to the left side and this number to the right side. So 3 log 5 of 3 times x minus x is equal to negative 2 minus 2 log 5 3. Okay, and we factor out x. And you divide the equation by the coefficient of x. This is the answer. Okay, so after the first step, that's just a simplification of a linear equation. Okay, you only have the linear equation. There's no trick stuff. And of course, we can. I mean, this whole computation is based on the idea in a previous example, first try. And we can also apply this alternative idea to this example. For example, let's try this alternative idea. So we start from 5 to x minus 2 is equal to 3 to 3x plus 2. We have this exponential equation. Then we directly apply the natural log. This is kind of a symmetric. Okay, it's a symmetric. We don't specially study the left side or specially study the right side. We studied both sides together with the same method. We apply the natural log. We apply natural log, and then by the same property, we can move this exponent forward. Now x and the numbers are in the same row. They are in the product, then we simplify it. Natural log of 5 times x minus 2 natural log of 5 is equal to 3 natural log of 3 times x plus 2 natural log of 3. I specifically put dot here because if I write this way, it's very close to the stuff like this. They're different. This one, it means I have natural log of 5 and then times x. X is not inside natural log. But this one means you have 5x and then you apply natural log. This is, I don't know what this is. It's close to this and it's also close to it. So this is not the right writing. This one is not a good writing. I mean, I cannot say it's not right, but it's not good. Not good. Okay, it's not a good writing. You either write this way, natural log parenthesis 5 times x, or you write natural log of 5 with a dot and times x. It means I'm trying to separate those two parts. Okay? Okay, I move this to the left side, this to the right side. So natural log of 5 minus 3 natural log of 3 is 2 natural log of 5 plus 2 natural log of 3. And you factor out x. And you divide the equation by the coefficient x. And this is the answer. They're the same thing. You can try the change your base formula. This is exactly the same thing. Okay? Next, let's try the some old type, the quadratic inform. We have 4 to x minus 2 to x and minus 12 is equal to 0. Here, 4 to x, 4 is 2 squared. 2 squared to x is 2 to 2x. 2 to 2x is 2 to x squared. So here, a to n and to m is a to m and then to n. If a to n, a to m both make sense, then you can switch the order of the exponents. Okay, so once you realize 4 to x is actually 2 to x and then squared, so you will let u be 2 to x. When u is 2 to x, u squared is 4 to x. So you get u squared minus u minus 12 is equal to 0. And then u minus 4 and u plus 3 is equal to 0. So u is 4 or u is negative 3. But after you get this, u is equal to 2 to x. The exponential function has domain, has a range positive. Domain is negative infinity, positive infinity, but the range is from 0 to infinity. So u is greater than 0. So this is u equal to negative 3 is not a solution. U equal to negative 3 is not a solution, so 2 to x is equal to 4. Well, 2 squared is 4, so x is 2. This one is a solution. Right? This one is a solution. Okay, so this is the section 6.6. Let me do more examples and we try to understand. For example, if we have four over 3, this is base to the power 1 minus x is equal to 5 to x, then what you can do, you can use either first idea or the second idea. So let's try the symmetrical way. We apply the natural log on 2 sides. And then we can move this exponent forward. And then we simplify it. And then we move this term to the right side. Okay, and then you factor out x. You divide everything by the coefficient of x. Okay, so this is the answer. You don't have to simplify it. Let me check if I make a mistake or not. Over here, it's positive, log 5 and plus this. Okay, I assume I got it right. In this section, there's also a part called solve logarithmic and exponential equations using a graphing utility. We don't allow any utility, so we skip this topic. Okay, so you don't have to do anything with a blue, not blue, green, with a green color. The problem number with a green color, you need the calculator. It is not allowed. Okay. Let's see this example. So if we have This one is good. 4 to x minus 10 times 4 to negative x is equal to 3. Remember, 4 to negative x is 1 over 4 to x. Okay? I possibly don't have enough space, so I use this part. So first, let's write it. So 4 to x minus 10 over 4 to x is equal to 3. Okay, it's a denominator, so you flip it to the denominator, you get 10 over 4 to x. You multiply two sides by 4 to x, so you get 4 to x times 4 to x is squared, minus 10 is 3 times 4 to x. Okay, you multiply two sides by 4 to x by this denominator. Here you have 4 to x squared. And then you move this to the left side, you got 4 to x squared minus 3 4 to x, and minus 10 is equal to 0. And this is a quadratic in form. So let u be 4 to x is greater than 0. Okay, the range of exponential function is greater than 0. Then this is really a quadratic form, the quadratic in form. And so u minus 5, u plus 2 is equal to 0. So u is equal to 5, or u is equal to negative 2. But u is greater than 0, so this is not the good solution. U is 5, u is 5, the 4 to x is equal to 5, so x is a natural, not natural, is a logarithm to the base 4 of 5. Okay, so this is the solution. So this section is not very long, but it contains some tricky problems. Do the exercise. If you have a question, we can discuss. Okay? Okay, we stop here. Thank you. We will continue in the next video.